every subset of size k has non-empty intersection. Ky is intersecting if every k sets and the family is maximal ky is intersecting if it's ky is intersecting, but no superset of the family is ky is intersecting. So if you add a set, then inevitably there's some other k minus 1 sets where those k, the new set together with a k minus 1 don't have any point that's in all of them. So ky is intersecting, but no superset or no larger family, no family that contains our family is ky is intersecting. And I'm going to be working exclusively with finite sets in this talk. So what I'm going to talk about today is a question of Erdős and Kleitman from 1974, which was how small can a ky is intersecting family be? So a maximal ky is intersecting family. Yeah, a ky is intersecting family could be empty or k maybe have, yeah. So that's one of the easier extremal questions, is how small can it be? Kleitman. And I'm just going to use the notation f of nk for the minimum over families over a base set of size n, which are ky is intersecting, of the size of the number of sets in the family. Maximal case one is interesting. Yes. So let me talk about some examples. A very simple example is a star. So let's take the set of the family F, which will be subsets of 1 to n that contain, say, one fixed element, say the first one. This is going to be, well, ky is intersecting for any fixed k and n large enough. Because if you choose any k elements, they contain the element 1. It's maximal ky is intersecting because the set that contains only the first element is in the So it's k-wise intersecting. It's maximal k-wise intersecting because this set is in F. So any set that doesn't contain 1 will be disjoint from this set, and it's already pairwise not intersecting. And the size of F is 2 to the n minus 1. So exactly half of the elements are in F. So I call this F sub S for now. Another example might be if you just take all the large sets. So what does large mean here? Let's say FL is a set well, if the size of every set in our family is at least k minus 1 over k times n, and I claim that this is a k-wise intersecting family. It's easiest to consider the family of complements. So let me just introduce some notation that I'm going to use for the entire talk, which is given some family F, the family F bar is the set of complements of sets in F. So if F is k-wise intersecting, that means that if you look at the complements, then the union of any k sets in that family don't cover the entire ground set. Because the common intersection of k sets is going to be what's missing when you look in the complements. And so we're going to say, well, how many sets of size n over k does it take to cover the entire ground set? This should be actually strict inequality. So how many sets of size less than 1 n over k does it take to cover the entire ground set? It takes more than k such sets. So certainly this is k-wise intersecting. And for certain values of n, this could be maximal k-wise intersecting. For example, if, if, say, n is congruent to 1 mod k, I think. Now, if you take n minus 1 over k, this, n minus 1 over k, you have one element left over. Any other set is going to have a complement that's 1 larger, and then you can cover everything. So this is an example, another example of a maximal k-wise intersecting family. And in general, the size is going to be much smaller, except for in the case of pairwise intersecting families. So except in the case k equals 2, this family is much smaller than the previous one. I think that's clear to see. In the case k is equal to 2, they actually have the same size. In the case k equals 2 and n is congruent to 1 mod k, they have the same size because you can pair off a set and its complements. In the case that n is odd. And then, in fact, this is generally true. So here's an easy observation. Is well, first pairwise any pairwise intersecting family has size at most 2 to the n minus 1. Well, let me, so if F is pairwise intersecting, over n, then cardinality of F is at most 2 to the n minus 1. And the proof here is for any set A, F is intersecting, so it contains at most one of A and its complement. So you can't have more than half of the elements of the, you can't have more than half of the sets over n in an intersecting family. In fact, there's something stronger is true, which is every maximal pairwise intersecting family over n has the same size. So if F is a maximal intersecting family, then the size of F is equal to 2 to the n minus 1. So now let's suppose suppose that F is some maximal pairwise intersecting family, and you have some set A that's not in F. So why is it that A is not in F? Well, F is maximal. That means you can't add A to F. That means, well, let me draw a picture here. This line is going to be the set of A elements, and here is here's A. The fact that I can't add A to my family means that there must be some set, say B over here in A complement that's disjoint from A. But the thing about intersecting families is that they're upward closed. If I take a superset of a set that's in my family, then that set must also be in my family. So we may as well just take the entire complement of A as the set that's in the family, and so we can see that, in fact, just using the maximality of the family F and the fact that it's intersecting, we get that the complement has to be in the family. And this proof generalizes as to k-wise intersecting. So let's say we have, suppose F is k-wise intersecting. And A is not in F. So I'm going to use this notation whenever I take the complement of a set or a set family or a family of sets. I'll just put the superscript C here. So this just means A is not in F. What does it tell us about, what does that, the fact, I keep forgetting to write Maximal. Well, since A is not in F, the fact that we can't add A to F means that in the complement of A, there has to be some k minus 1 families that intersect. So here we've got B1 intersecting B2 intersecting intersecting BK minus 1. And as I already noted, all of these families are upward closed. So again, we may as well take the complements. And this actually defines an injection from sets that are not in our family into k minus 1 tuples of sets that are in our family. Because given B1 to BK minus B1 to BK minus 1, you look at their intersection, and the complement of that is the preimage of those k sets. So this tells us that the size of FC is at most size of F, choose k minus 1. And this is equal to 2 to the n minus the size of F. And an injection, yes. So the thing is that we can, if I give you some sets B1 to BK, you can tell exactly what any candidate for the preimage of that, you can tell it's just the complement of their intersection. So given B1 to BK, let's just take k minus 1 sets in F and not worry about is it in the image of this map or not. If you take their intersection, they must have an intersection because it's ky is intersecting. You look at their intersection and you look at the complement of that. And then if there's any set that maps to this k minus 1 tuple, it has to be that set. So if you have a set A and A prime that aren't the same, they can't map to the same k minus 1 tuple. Right, yeah, because, yeah, exactly. So we use the upward closeness to ensure that there is some k minus 1 tuple whose intersection is exactly the complement of the set that we started with. So this gives us a general lower bound, say, on f of nk. We know that every set family that every maximal ky intersecting set family has to have size at least, say, 2 to the n over k minus 1. Because here you get, this is bounded above by f to the k minus 1 over k minus 1 factorial, and k minus 1 factorial is at least, well, let's suppose k is at least 2. I think this is right. And in particular, in the case, I think I'm mostly interested in the case k equals 3. We'll see that we really only get good results for 3-wise intersecting families. In this case, if we do it a little more carefully here, we get a 2. So there's 1 minus little o of 1 accounting for this f. And here's f squared, divide by 2, taking the square roots, in this 2 to the n minus 1 over 2. So that's some non-trivial lower bound. And it's almost tight for the case k equals 3, or at least you'll see it's not too far off for k equals 3. Let me give the example. So linked cubes is what we call this example. But let's take this family. Well, let's take sets y1 to yk minus 1 that partition and we'll make them as close to being equally sized as possible. Then the family F is going to be the union over I of proper supersets of the union of the other families. So let's say so union over I of the sets A that contain the union over J, J not equal to I. So if we have here is the base set N, we've split it up into evenly sized blocks, y1, y2 to yk minus 1. The sets that we're going to have in the family, each of them is going to have all completely contain all but one of the underlying sets, and these are proper. It's important these are actually proper supersets. Yeah. And then have some non-empty intersection in the last section. And so we'll have other sets that look like that, etc. So now, what can we say about this family? Actually, I'm very sorry about this. I'm going to change notation. Because I don't want k here because I want it to be k intersecting, but this is not going to be k intersecting. I'm going to just put t. Every place I put k minus 1 before, I'm going to put k before, I'm going to put t. Yeah. Because this is, yeah, I'm sorry about that. Observation 1 is that this is F is 2t minus 1 intersect. Let me draw just the picture for t is equal to 2. And let's look at three sets. Say A1, A2, A3. Well, each one is a superset of one of these two halves. So we may as well assume that A1 and A2 completely contain this side, and they have something else on the other side, which may as well be disjoint. Then A3 has to contain something on the same side that A1 and A2 completely contain because it's a proper superset. It's either a proper superset of Y1 or a proper superset of Y2. In either case, it has non-empty intersection with y2. And so there's some point in all three. And similarly, if t is more than, if t is larger, you can think, well, pretty much we're going to take some sets to, we want to, say, kill this last section. We're going to kill yt. And it will take us at least two sets in the family to do this. And once you have these two sets in the family, then it doesn't matter. All the rest of them can completely contain this section. But so if you want to kill the entire underlying set, you're going to have two from each subfamily. And so that's why we have it's 2t minus 1 intersect. And in fact, it's maximal 2t minus 1 intersect. So here we need to kind of consider two cases depending on what set we're adding. So case one is that the set is completely misses one of the underlying y's. Let's say we add a set that just doesn't intersect yt at all. And it has, we don't care what it has elsewhere, it just doesn't intersect yt at all. So let's say B intersect yt is empty. Well, we already killed this set here. So in particular, in this specific case, we can then kill the y1 with just two sets. But in general, we've already seen that it just takes, we can, for each I, we can kill yi with just two sets. So this gives us a way to get 2t minus, if we take B as one of our sets together with a pair of sets for each of the other I, this will give a set of 2t minus 1 that's not intersecting. And another case to consider is that there are at least two I such that where B doesn't contain the corresponding yi. So we have some intersection here and we have some intersection here, but we don't properly contain either Q. So B intersect yt is not equal to yt. B intersects yt minus 1 is not equal to yt minus 1, for example. Now, of course, we need to add two more sets, but this means just that we can kill yt with one additional set, and then we can kill yt minus 1 with one additional set. So we have this. And here this one has that one completely contained. And this one completely contains that set, but it's disjoint from whatever's over there. And this is the picture of what's going on here. So it's maximal t minus 1 intersect. Next question is, how large is it? Let's just assume that, let's take, so if t divides n, just to make it easy, then the size of this particular family is t times 2 to the n over t minus, well, 2 to the n over, yeah, 2 to the n over t minus 1, and then minus t minus 1 again. The point is, here we don't have the empty set. We're taking subsets of each yi. There's t choices for the I. We take all the subsets except for the empty set. So there's a minus 1 here. And then we've overcounted the set of all n elements. And so we've counted the set of all n elements t times, so we have to subtract out the overcounted. So this is the exact size, but it's not too important. The more important thing is that what this gives us is an upper bound of 2 to the well, let's see, if 2t minus 1 is equal to k, then t is equal to k plus 1 over 2. But this is what it is for odd t. And the unfortunate fact is we don't know of any better construction for even t, except for just take the previous construction for odd t. So we may as well just put a 4 here. So n over k plus 1 over 2, 4, and then times some constant. And here, so what is our lower bound is n over k minus 2 to the n over k minus 1, and the upper bound is 2 over k plus 1 over 2. 2 to the n over k plus 1 over 2. So we have basically a square root difference between the upper and lower bound. Except in the case that n equals 3. Here, if I'm going to do it a little bit more carefully in this case, just as I did before. Just because it's actually, instead of being off in the exponent, we're only off in the constant here. So this gives us an upper bound of 2 times 2 to the n over 2 minus 3. So 2 to the n plus 2 over 2. Is that? I feel like there is something not quite right here. This is supposed to be a plus. That's supposed to be So for the case k equals 3, this gives upper and lower bounds that are already, this simple argument gives upper and lower bounds that are within a factor of square roots of 2. And for k equals 4, we already don't know the right exponents. It could be 2 to the n over 2, or it could be 2 to the n over 3. And we don't know in the case k equals 4. So our main project here is, wow, I've already used over half of my time. That's unexpected. The main project here is improving these kind of crude bounds in the case that k is equal to 3. So let me just write the theorem. Here. So theorem 1.1. If n is even, right, in this, for this calculation here, I assumed n was even. And in fact, it's a little bit we don't get the same constant if n is odd, because there we get ceiling of n over 2 of all subsets of a set of size ceiling of n over 2 and all subsets of the size of set 4 of n over 2. And this is a different leading term of that.
I guess the lower bound is
No, it's upper bound. It's upper bound. Upper bound is a construction, and the construction is, we can only get this type of construction if n is even. Yeah. So what we do is we really say that in the case that n is even, the extremal example is exactly this this linked cubes construction. So if n is even and f is a maximal set 3y's and the size of f is at most 2 to the n plus 2 over 2 minus 3. So that's the size of this construction. Then f is a balanced pair of linked cubes. Which is simply the construction that I just described. And we have a kind of stability theorem here that also gives a result for odd n, which is for all epsilon greater than 0, there exists an eta greater than 0 and an integer n0 such that if n is large enough and f is a maximal 3y's intersecting family, the size of f is at most 1 plus eta times 2 to the n plus 2 over 2. Then n is even. And at most epsilon times n and all but epsilon n sets are contained in a balanced, all but epsilon n sets of f are contained in a balanced pair of cubes. Not epsilon n, but epsilon times the size of it. All but an epsilon fraction.
So the sufficiently large n should also be the theorem of
Yes, theorem 1.1 also needs sufficient. F is even and sufficiently large. Thanks. Right. So the first step, or the kind of key idea which we use, the first step in proving this is to observe that we can actually get an injection not only into, we're going to again define an injection from the complement of F to now pairs of sets in F bar. So recall that F bar is the set of complements. And what we're going to gain is that the sets, we're always going to send it to pairs of disjoint sets. And this disjointness is the key property that gives us a handle, that gives us a handle on improving the crude result that I showed before. So the idea is, suppose that we have A is not in F. So it's in F complement. Again, F is going to be a maximal three-wise intersecting family. So as we observed before, we can find some B1 and B2 in F, so that B1 and B2, B1 intersection B2 is equal to A complement. So here we have, maybe I'll make B2 pink here. And over the, so they're distinct sets, so they have something going on inside of A as well. But they both completely contain A complement. Well, as we observed before, the set F is upward closed, so we may as well take the, if the union of B1 and B2 is not the entire set of all n elements, we may as well increase the size of B1 and B2 until it covers everything. So now here's B1 and B2. So what the complements of these look like is exactly, but now the complements of the sets are disjoint, and their union is exactly equal to A. So here's B1 complements, and here's B2 complement. So, and of course, given B1 complement and B2 complement, we can easily recover A because that's just the union. So this, let me introduce a notation for disjoint pairs. Disjoint pairs for some set, let me call it G now because is equal to set of unordered pairs such that A and B are in G, and A intersect B is equal to the empty set. And this is what we call the disjoint pairs in B, or in G. And we have an injection. There's an injective map from F complement to disjoint pairs of elements in F bar. So in particular, we could say the size of F complement is at least, and this is equal to 2 to the n minus the size of F, which is always equal. Sizes F and F bar are, of course, the same size. Is at least the number of disjoint pairs in F bar. So what we need to do is get a stronger lower bound on the number of disjoint pairs than just, well, obviously the number of disjoint pairs is at most the number of pairs. But we can get the disjointness gives a handle on improving that. Yeah, unfortunately, I'm almost out of time here. So 5 or 10 minutes, yeah, 5 minutes. So the way to maximize the number of disjoint pairs is basically known from previous work. We have say a series of cubes. Let me just state things for the case that we're interested in, where there's a pair of cubes. So a pair of cubes are the sets F is equal to, we have some sets, let's call it A subset S in A subset S complement. So this is almost the complements of a linked pair of cubes. The only real difference is that, so here we're looking at, we've got some partition of our ground set into A and A complement. And we're looking at things that are completely contained on one side or completely contained on the other side. And these are clearly the complements of supersets of 1/2. The only real difference is that here we are allowed to take the entire set. So it's not quite the complements of the linked cubes that we talked about before, but it's very close. And there's a theorem of Lund and Frankel that says that this is for the in the case that you can, well, for even n, say, this is the way to asymptotically maximize the number of disjoint pairs. And we also have a stability result, which I can and we also give a stability result which says that if n is even and you have as many disjoint pairs as you would expect from this construction, then it must be in fact a pair of cubes of this type. The proof of this is, I mean, nobody has written it down before, but it's based on earlier work of, let me get the list of names right. Lund, Das, Glebov, and Sudikov, who worked on a very similar problem of force. How do you maximize the number of pairs of sets where one is contained in the other? In that case, there's a different extremal construction where you take what they call a tower of cubes. So you split your base set into a bunch of sections, and you take all the subsets of the first one, and then now you completely contain the first section and and add to it all subsets of the second, and you completely contain the first two, and this is, if you want to contain pairs, this is how you maximize it. But anyway, I don't have time to give the full details, but this is kind of the first step of the proof here. I'm willing to take questions. In the meantime, I'll write down our theorem on disjoint pairs. If there are any questions, feel free to interrupt me. It's in the paper. The paper is on archive, so if you're interested, you can see everything there. That one's a series of cubes. So this is a pair of cubes. You can, if you had more than two, if you partition your ground set into k sets of even size, then it's, you know, it's easy to come up with a lower bound on the number of disjoint pairs, because you choose a pair of cubes, and what's the chance that they land inside the same cube? If they don't land inside the same cube, then they're obviously disjoint. If they do land inside the same cube, then we don't care. This is some very much lower order of term. So the probability is basically 1 minus, or the number of pairs that's disjoint is going to be 1 minus 1 over k. If you choose one, there's a 1 over k chance that the next one lands inside the same cube. And what this says is that if you have any set family that has almost as many disjoint pairs as possible, then in fact k does divide n, and the underlying set family looks very much like a series of cubes. And so that's the end of my talk.
Is there some different version where instead of saying the intersection of k sets are non-empty, maybe if you replace with the intersection having size and is t, then do you get something like that? Threshold version?
Let's see. The answer is I haven't really thought about it. That sounds like an interesting question. I imagine it must be open because this one is open. I don't know whether that would be. I don't know if. Do you know anything, Casey?
External problem where you're maximizing location data and
It's still somewhat open for arbitrary parameters where you let n be anything, ky is intersecting, where the k things have to be at least t in common. There's various constructions that are almost better in some regimes.
So here you could, for this you could always take a Coro size t and take out every superset, but this may not be the unique maximum.
You could take a star with a core size, or sunflower with a center size t. But that would be what I would guess would maximize
For the extreme or for maximizing the size. Without worrying about, but the stability version, I have no idea.
Actually, for the extremal version, usually you want to take the large.
You take the large
sets as large as you can take instead of star-like things. It's usually better because you get that positive chunk of the Boolean matter set, right?
I don't know.
But for saturated, I don't think anybody is. Because already this is difficult, so I don't think.
I mean, for pairwise intersecting, you could get a positive chunk of the Boolean
Lattice by taking the large sets. But if you require, say, every 3 to have common t elements in common, then even to get one element in common, you can't take a positive chunk of the Boolean lattice by taking the large sets. Whereas if you take a core of size t and t is not too large, I mean, it's complicated, right? It depends on the parameters. Well, you think it's known though. You don't think it's known, even the large. Yeah. So for the stability version, you don't think anybody's probably nobody's considered it, because if they had, they would have already considered this problem as well.
Thank you. Okay, if not, let's thank the speaker again.